I've got n is equal to the guess, excuse me, n over the guess is equal to h. And then g plus h over 2 is equal to the next guess. That's all we've got going for us in that program. Well, in that case, we've got n equals gh, and the square root of n is equal to the square root of gh. Ah, there's that geometric mean, isn't it? The square root of gh is the geometric mean, and what we're using for it as an estimate is the arithmetic mean. What does that mean? First of all, it means that the next step, the second guess, has got to be greater than the square root of n, right? Because the arithmetic mean is greater than the geometric mean, and the geometric mean is equal to the square root of n. So we've got this situation. So we've got a guess up there, and we want to find a way of showing that what we're going to get is going to shrink down toward the square root. All right. So we know now that our guess is greater than or equal to the square root of n. What about the h that corresponds to that? Remember, that's the number you get when you divide n by a guess. Well, let's see what happens. I'm going to take the reciprocals here. And what happens to an inequality when you take reciprocals? It reverses, right? Okay? And if I multiply each side of that by n, the left side is h sub n, and the right side is square root of n. So when g is larger, h is smaller for every step. All right? Now, I'm going to take that last statement, and what I want to show here is this. I'm going to call the error the difference between our number and the answer, so that at any step, e sub n is equal to g sub n minus the square root of n. So that e sub n plus 1 is equal to g sub n plus 1 minus the square root of n. All right, now let's see if we can work simply from this statement and get something like that. All right, I'm going to do the following. I'm going to add to each side g sub n. And I'm going to divide by 2. And what does that do? What does that make the left side? When I take the average, I get the next guess, right? Okay, so the left side is g sub n plus 1. That's 2 over 2 there. So I get g sub n, and then plus 1 square root minus 2 of them. And that right side numerator is e sub n. So what have I shown? I've shown that e sub n plus 1 is e sub n is less than or equal to e sub n over 2. What that means is that every step here I get at least halfway to the right answer, and as you know, when you do that dividing by 2, you converge very rapidly on a value. And that's exactly what's happening in this program. I'm sorry I'm hurrying a little bit because I've used more than my share of time. Let me finish up. I began this talk indicating the difficulty of writing math. I'll end it by commenting briefly on reading math. A number of people have offered suggestions. Here are a few. Slow down and reread where necessary. Follow math arguments with paper and pencil. Seek out the meaning of unfamiliar technical vocabulary. Carefully associate text and diagram. Well, look, I support all of those suggestions, but I don't believe they solve many of the communication problems that arise. For example, I find that assumption that rereading will solve your problems often unproductive. You may just recycle like a scratch DVD. But I suggest there's still another approach that may help. You too reader and writer, need to form a compact to reduce your differences and turn your reading into a cooperative adventure. This happens too seldom, even in the classroom, when students and teachers are face to face. I was very fortunate to have a number of fine teachers with whom I felt I had such an unwritten compact. And as it happens, one of them is here today. Arthur Denise taught me differential equations at the University of Rochester before he came to finish his teaching career here at Fredonia. Art, I finally get to thank you today in this public forum. Art Denise. Please understand that what I'm calling for here, math writing is not like a legal argument with the expositor trying to convince you of points about which intelligent people will disagree. I know of no mathematics writer who's trying to dupe readers so you and the reader are on the same side. This may seem like an oversimplification, but I urge you to try adopting this attitude on some mathematical exposition. Try it on my book or on the others I'll name in a moment. I suggest that as you read, you mark in the margin each place where you don't follow the author's argument. If you find your margin festooned with such marks, that text is too tough going for you, and you should either give up or seek a mentor's support. On the other hand, I think that you'll find that approach appropriate text in this way, you will not need to make many marginal marks. I did this myself recently with a book that I found rough going when I first approached it. It's Paul Nahin's When Least is Best, an outstanding book, but not one that I recommend to neophytes because it requires an understanding of the calculus. But when I relaxed my demands on myself, that I justify every step in his exposition, I was pleasantly surprised by how this simple change in approach improved my understanding. I ended up with remarkably few marginal ticks. I found that in fact, the very fact of stopping to mark a tick usually led me to find a way to bridge the gap I was annotating. What I think happens when you make this kind of pact with the author is that you become a colleague in the enterprise of communication. You're no longer in a subservient role or even an antagonistic role. You and the author are now on the same side. I close these remarks by listing you 7 books, including my own, of course, largely accessible to the general reader, even those with only a minimum background in school algebra and geometry, on which you might try my suggested approach. They're books that I believe belong in libraries. In a few minutes, I'll change and give you some references so that if you have any questions or